Hello, this is Sharon Fisher, and Teledyne ISCO would like to thank you for joining us for our webinar, Flowmeter Billing Accuracy. To cover a quick housekeeping rule, if you have any questions during the webinar, please utilize the Q&A function within Zoom. All questions will be answered at the end. This webinar will be recorded and a video will be made available on our YouTube channel in the near future. Today, we are lucky to be joined by two of our water platform experts, Bob Glenn, Western Regional Manager, and Rick Dye, Business Development Manager. With that, I would like to welcome Bob.
Thank you, Sharon. Welcome, everyone, and thank you for joining us for this presentation. My name is Bob Glenn, and I'm one of the regional managers here at Teledyne ISCO. Before I hand it over to my longtime friend and colleague, Rick Dye, I wanted to share a few things about our company. Teledyne ISCO is located in Lincoln, Nebraska, and was founded in 1958. Teledyne ISCO is a true manufacturer, not just an assembly house. We take great pride in the manufacture of rugged instruments used by professionals in the water, stormwater, and wastewater markets to protect water quality all over the planet, and have done so for 50 years, having developed the world's first automatic wastewater sampler in 1971. As we enter our second half century, we remain a world leader in the field of automated water sampling and open channel flow measurement, and we remain as committed as ever to finding new and exciting ways to apply our products to safeguard the world's water. The recent use of our sampler products in wastewater-based epidemiology studies geared towards early detection of coronavirus is just one example of how our products continue to be applied in the water monitoring market to benefit mankind in this rapidly changing world. In today's webinar, Mr. Rick Dye, Business Development Manager for Flowmeter Products, will discuss flowmeter billing accuracy and how to interpret flow data using advanced diagnostic capabilities. He will also offer some great insights and tips from his more than 3 decades in the business to evaluate flow metering problems and minimize frequently encountered mistakes, which can significantly impact billing practices. We hope you find today's webinar educational and insightful, and I urge you to reach out to myself, Rick, or ISCO's product support and service group if you have further questions or need assistance with any aspect of your flow metering project. With that said, I'll now hand things off to Rick. Enjoy the presentation.
Thank you, Bob. We'll go ahead and get started. As Bob mentioned, my name is Rick Dye. I am Business Development Manager for Teledyne ISCO in the Flowmeter product area specifically. Probably talked to a lot of you over the years, and appreciate all the business and everything and the relationships we've had. Today, what I'm going to talk about is something very important, which is, how do I verify some of the accuracies I'm getting or my data that I'm getting, especially related to billing type of applications. We get this all the time. People want to know, hey, I'm going to pay somebody for this. How do I know it's right? I'm going to get into some fairly high level technical stuff on how we read some of this stuff. But for now, let's go ahead and let's kind of just, why do we measure flow? What's the purpose? Inflow and infiltration studies, or INI studies. If you're from Europe, you might refer to those as flow surveys. Bottom line, we're looking for rainwater getting into our collection system. That should not happen. So we put flow meters out there to measure that flow, to attempt to figure out where we need to put our resources and money to fix those problems. Another one, enforcement requirements. So industrial pre-treatment, we see that all the time. I'm going to put a industry here, and I need to pay for that water that's going to be treated. So billing accuracy also for water custody. So here we're discharging water to other treatment works. So a lot of cities that do that, that's very common. Atlanta, Phoenix, Milwaukee, Boston, you name it, Denver, and the list goes on and on and on. So somebody's discharging water, somebody has to treat that water, they're paying for it. So the more accurate they can be, the better off for everyone around. Okay, so here's kind of a good shot of a flume application. This is actually going to the influent to a wastewater plant, but another community is billing for this. You'll notice there are multiple sensors in this channel. They have actually two different ultrasonics, and then they have a laser at the inlet, influent to this channel. So what they're doing is they, when everything is good, no problems, their flume is accurate. When and it's not good, due to a surcharge or plugging or blocking of that channel, then the flow is not going to be accurate. They're going to end up paying for that. So flumes a lot of times are used in pre-treatment applications where you do have a wide range of flow conditions. And because of that, you can have you might have to have the ability to measure very low flow. And in that case, you can have blockage or plugging in that throat of that flume. So you may need to clean that. I've talked to people that said they clean their flumes every week. So that's a fair amount of maintenance if that's true, and you have to do that. So this is a big one, surcharge flumes or submerged flumes. More and more common. People developed or designed based on what they knew from years ago. And now the flume can't handle the amount of water that's going through there. So we start getting some surcharge conditions. Now, the one advantage of a flume is that it really only needs a level measurement in order for it to give you an accurate reading. So very easy to do that. You just stick a ruler down in there and you get a reading and away you go. So provided everything is good on the flume side, as far as the installation is good, there's no inaccuracies of the elevation of the flume, and the approach section's good, and we don't have surcharge downstream. All those conditions can affect it. So if those are good, then everything is good. Flumes have been around forever, and a very good way to do it, but they're not infallible. And sometimes you could run into some issues. So in this case, they have a laser upstream. They're measuring the flow with both. When it does go under surcharge, then they would switch over. If the flume is properly installed, you can expect about a 5% accurate reading. So 5%, within 5%. So Weirs. We see a lot of these out there. Weirs are very easy to design and build. So it's very basic thing. It's inexpensive, obviously, piece of wood. In this case, they have just kind of a stainless steel face on it. They're going to be reasonably accurate. If a weir is installed correctly in the correct location, you could expect, again, roughly in the 5% range. These can be tricky to install depending on what they're doing here. In this case, these guys were installing in an actual manhole, which is going to be very, very challenging. It's going to also dam up the water. So now you're putting a dam in the flow and you're backing it up. So not typically desirable in sanitary lines. Accuracy is going to be questionable. What rating curve are we using here? So this doesn't really match anything that I would look at from the ISCO flow handbook. So again, bottom line, we take a level measurement for most of these devices. Once we know the level, we can look at our ISCO handbook, make sure we calculated the flow right, that it did the math correctly. Okay, so this kind of some older pictures. Maybe some of you have seen these out there, but on the left, that would be a flow meter. That was one of the older style full-blown flow meters, had a built-in printer, keypad, and display. One on the right is a flow logger, and there are a lot of different types of flow loggers out there. And what those do is they wake up, they take a reading, they store it, they go back to sleep, and they don't know what's happening until the next reading interval. So these are kind of a couple different styles that you may encounter over the years. And one thing again that is very popular is they only need a level measurement if they have a primary device. So let's talk about some equipment options now. Obviously, you need to determine if you have permanent power or main power, AC, or are you going to run it on DC? What kind of meter choices are you looking at? Are you looking at a portable meter, possibly a permanent meter? Some people call those flow transmitters out there, a lot of different types of those as well. And so again, looking at a Flume or a Weir primary device, very simple, and a level measurement is all that's required. So in order to maintain accuracy on that, you can just go around and verify that your level is correct. If your level is correct and the Flume is installed correctly with the proper hydraulics, you should expect about 5% accuracy. All right, let's talk about some of the more advanced technologies out there. This is the Flow Lab at ISCO, Teledyne ISCO. If you're ever in Lincoln, we encourage you to come by. We'll be happy to give you a tour. This can run anywhere from 4-inch up to 24-inch pipes. We use this for development, really. When we design a new product, we run a million tests on it, and we want to make sure it does what we expect it to do. And this Flow Lab is certainly one of the advantages I think that we have to be able to run that. But we use it for training and different things as well. But let's talk about area velocity, because that's one of the reasons we did come up with the Flow Lab, was we wanted to be able to develop a very good area velocity system. So area velocity, Q is your flow, is equal to the area, which is a level measurement, and that's done typically using a pressure sensor or an ultrasonic sensor. So for those of you that might be familiar with the 2150, we use pressure primarily with our stuff. V is a velocity component, and that's typically a Doppler type style or Doppler technique. There are a couple different ones. One would be a contact, which is a sensor that's actually in the water. Another one would be a non-contact. So we're talking subsurface, or I'm sorry, out of the water technique. So we may use radar, we may use laser or whatever to measure that velocity. Okay, so look at this, a little bit different picture. I kind of like this one because it gives you a better view of what this thing is doing. So you have a sensor that's on the, or in the flow on a ring. So it has a stainless steel mounting ring. It measures the water level. Once it knows where the water level, we take a velocity reading using, again, a continuous wave Doppler style technique. So these are going to be very good for the most part, very accurate, but they have their limitation. This is a kind of a better view of something that a grad student did for me years ago in Italy. And I kind of liked it because it gives you an idea of what that signal looks like. So when it's transmitted out the nose, it's a fairly small, tight point or tight beam. As it gets further away, that beam gets bigger and bigger and bigger. So as a general rule, I would say we're looking at roughly basketball size, depending on the depth of flow. With an area velocity, what I would expect to see would be something in the 5 to 10% range, depending on how deep the flow is. So if it's within 2 feet, you're probably going to get in that 5 to 10% range. So let's look at what does this thing actually see. This is kind of a good shot too of a what we would call a Doppler signal coming back. And this is a return spectrum. So if you look at this, what we do is we transmit, we sample that return signal, and then we take what's left, we trim off the front back end of it, and we calculate the average velocity for that point. So this is a good way to do it. Again, it will do very well. As you get deeper and deeper flow, you will tend to underestimate the velocity with any technique like this because it just cannot see up into the flow like a different device might. These readings are all stored in memory. So we store what we call signal strength, spectrum strength, and spectrum ratio. We have a very, very good white paper that is available to you if you want it. I'll be happy to get it to you, but it will give you a good description of what I'm talking about. And that's, you should be able to just go online and download that. but this is a kind of a cheat sheet that we set up for a customer one time. And they wanted to be able to look at this and kind of get an idea of, okay, if my signal is 20% and my spectrum is 10, I'm in the E category. E means I have a weak signal, spectrum strength, poor application, data is suspect. So ideally you want to find a different place. So kind of a neat, nice little cheat sheet here for you to be able to determine, if my application is good or not. Okay, so some of the most common mistakes that we see, the most common is a really bad application. Nothing's going to work. So you can't make everything work in every application. So if you have something that's ridiculous, water's coming in from the side, dumping into a flow channel, nothing's going to work. And you really are just going to have to find a better site. Overcorrecting for level measurement and field verification. This is a big one. So people will go out and they will do what I call the chase your tail syndrome. You put every one of us in the world out in a manhole, we're probably going to get a slightly different measurement. So we want to be a little careful on how we correct for those level measurement and make sure that we don't, again, chase our tail. Handheld velocity measurements. We see a lot of those out there. The technology is a sound one. It's typically electromagnetic, and those have been around for quite a few years. Again, very sound, but I would be careful that I use it any more than just kind of a sanity check. With what you're going to see with some of the new stuff like the laser now and things like that, is going to be far more accurate than anything you would be able to get with a handheld device. All right, so let's get into non-contact. So why would we use a non-contact sensor? Obviously, right here's a very good example. We don't want stuff on a sensor. It doesn't matter who makes this, it's not going to work. So we want to make sure we don't have that. Safety is also a big issue. Nobody wants to go down on that manhole if they can help it. So we want to do everything we can to keep people out of those manholes. All right. So what we want to make sure, though, is we provide the right product for your application. So when we look at all of these, we want to make sure, hey, is non-contact the best solution for you? Maybe it is, maybe it's not. So we want to make sure, again, that we evaluate your application and give you the right product for it. So let's talk about laser and how it works. So you have a sensor that's in the back of the unit itself. It uses a ultrasonic to measure the level or the distance to the water. So it knows where the water is. Once it reflects off that, then it knows where it wants to focus the laser. So the laser is actually doing two readings. It's doing a level reading and it's doing a velocity, but it does the velocity subsurface. So it's below the water surface itself. Another little kind of idea of what it looks like. So if you look at it from the front view, side view, what you'll notice is if you stuck your hand underneath it, you'll see a dot, the size of a quarter or coin. And where it actually reads or takes its reading is a very focused point. So when I look at a laser on the flow, I want to make sure I have a very, very tight laser beam or laser point on that flow. That is known as converging section or point of convergence. And we take 5,000 velocity readings in 2 seconds. So to kind of give you a little comparison, a standard area velocity takes about 500. This takes 5,000. So it does it in a very, very short amount of time. This is some of the stuff that I look at. And this is the diagnostic that supports the reading that you're going to be getting. So when I look at this, there's a couple things I look at. One would be what we call the X angle, the Y angle. That is the pitch and roll of that sensor. So like a cell phone, it knows where it's at. So we want to make sure we are level. X is 0 plus or minus 3. We're right on. Y is 45 plus or minus 3. And we are, again, right on the nose. And what we're looking for is this. So this is the return signal coming back from the laser. So the more that agree on the return signal, the bigger this looks. So now with certain confidence, I can look at this and say, this thing is working right or it's not. And when you're looking at billing applications, this is one of the most important things to be able to look at to say, yep, we have a good reading, or no, we don't. It also would tell you if it does go underwater, if I have to do any maintenance on it. So right now I can see there's nothing that needs to be done with this unit itself. These are also made into a value that's a little easier to understand. So for the typical user, you can look at here in this case, I have level, I have my velocity in meters per second. In this case, I have my Doppler power here. So anything above 1,000 is considered good. You'll notice the level went up, the velocity went up, and now all of a sudden my Doppler power or my velocity both dropped. So that would tell me there's probably something in that channel that's either covering that or possibly surcharging that sensor. So again, very, very powerful diagnostic information to be able to use to determine if it's good data or not good data. All right, so a couple ways to set these things up. One would be we do a level measurement. Once we do a level measurement, we're able to scan across and do up to 15 different points of velocity. So now I can scan across that and see each individual point. It does not do a complete velocity profile. So for those of you that might be familiar with the old ADFM technology, it does not do everything that does, but it does a pretty darn good job, and it's going to give you a roughly a loaf of bread is kind of the way I describe it. So if my hydraulics are very uniform, it doesn't matter. You probably don't need all these points. If you do have some irregular hydraulics there, you might want those. It really is all about power. So power and time to reading. It's going to take more power and it's going to be slightly slower getting you those readings. This is known as a multi-point, multi-depth velocity method. So I'm going to show you some application shots of where we use some of these. Give you a little better look at some of these applications. So collection system is what we designed it for. We looked at what we called large pipes would be anything greater than 36. And then we decided basically a small pipe is anything less than roughly 36. 36 is still a pretty good sized pipe. But we designed it for both large and small, and we're seeing a lot more small pipe applications. Okay, so some of these applications we're looking at that are going to be very difficult for, let's say, a flume would be a high velocity, low level. So that water's coming down the hill, making a steep run at it. It's going to go splashing everywhere. So a flume is not going to work, where you might need a non-contact device such as a laser. So steep slope pipe, low level raw wastewater. So anything less than 1 inch is going to be very challenging because you just don't have much to work with. And pretty much every area velocity sensor that's in the flow needs 1 inch to work. Anything slower than about a ½ foot per second. When you get down below about a ½ foot per second, that you also will see a lot of times in residential collection systems, that is going to be very, very challenging as well. Slow clean water effluent to wastewater plants that you might be getting billed off of chlorine contact or UV disinfection channels. Drinking water influent, that's another one that we're seeing more applications where they need to pay for the water that's coming into a drinking water plant. So it's raw wastewater or raw water. Stormwater, again, wide fluctuation in flow conditions. Something with an irregular shape channel is going to be very challenging. So here's one where we have a low level, a high velocity application. So this is one city that's discharging to another, and they have to pay for that. Well, this is a very, very challenging application, and really using a non-contact would be the best way to go for them. The typical laser and some of the other stuff you might see out there, roughly about a ½ inch for velocity, and can read about 15 to 20 foot per second, depending on what technology you go with. So here is a good picture of one that's installed. It can be pointing into the flow or downstream, it doesn't care. But you can see that this would be a much more appealing application or location for a non-contact than something down in that flow. Another shot of one that looks like glass. You can see the surface is very smooth. This would be a very slow application, which makes it very tough, very difficult to be able to measure. Okay, so if I don't have a flume, I'm going to go area velocity. It'd be nice to be able to have it in a kind of a round pipe where I have just a small opening. So this happens to be the flow lab, so you can see where the opening is on the top, but this is where the laser is actually hitting. In the real world, this is a great location because now I have a nice hydraulic condition. I have a round pipe, almost full. I just have a nice little notch at the top. The ultrasonic level is going to be read right below the handle roughly, and the velocity be read right out in front of it. So this is a very, very good location. And ideally, if you can do this, this is going to be your best billing location or billing application. So again, industrial monitoring, you can see the laser on the flow itself, but anytime you can do this would be preferable. Okay, here is one that's a actual shrimp factory in Louisiana that's discharging to the bay, so they have to pay for what they are discharging. You'll notice there's just a nice little opening in the top of this PVC pipe, shoots right out the end of that, and away they go. So very, very easy way for them to measure that flow. Here's another one. This is an industry in Las Vegas, and they are discharging that water. You can see it's moving through there pretty good. So they didn't have much of an area to be able to install anything. So tight spot, but they were able to get the meter in there where they needed it. Okay, here is a effluent discharge, which again is a billing location for these guys. There's 2 bolts that hold the bracket right there, so it's easy to install something like that. Here's one that is a very challenging location. This is one where the water's coming over a hill or coming over this wall and then going through this very difficult location, a lot of entrained air. So initially we didn't know if we were going to work, but I wanted to show you this because this kind of gives you an idea of the power of some of the diagnostic capability. So the bottom left over here, you'll see is a picking up low frequency return, which is from the entrained air. So occasionally what it would do is it would start dropping velocity readings or giving you real low readings. What we're really looking for is this over here. So if they were paying for this or billing off this bottom one on the left was going to give them inaccurate data, and they would be paying way underpaying for their water treatment. So what we were able to do is change some of the settings in the program and ignore this to the left of where this circle is, and now focus on the right side, which is where the true velocity is. So diagnostics in this case helped us figure out what was going on, what was real, what wasn't. So big deal here. Once we made that change, you'll see to the right of that bar is what the data looked like. So the left side was pretty much garbage kind of data, and the right side, once we ignored that low frequency, now we are getting very, very accurate data, and the customer is happy with what they're seeing. Okay, here's one that's a very clean application, but it's a UV channel from one of the industries that was discharging, and you can see that water is very, very clean. So another one that's a difficult application. Here's one where they had a drop pipe, so the water actually is creating 2 different levels. So in this case, the laser would want to read where it's free falling out, and they want to read actually up in that. So that wasn't going to work so well. So what they end up doing was getting a remote ultrasonic version of this. And the sensor now is mounted horizontally, reflects off the water in the pipe. So now we're getting a much more accurate representation of where we're trying to take our velocity reading. Other application, which was very challenging because it's kind of coming around a bend, but they installed a remote ultrasonic in front of it. And in this case, the laser is shooting down in front of the laser where it's actually reading its ultrasonic level. So a good place for a very accurate measurement. These become challenging. So when you have something like this, where you have a very, very wide channel, but in the middle, you're very narrow during normal flow. This happens to be Southern California. So they're using this to determine water flow from one area to the next. So once they're low flow, they're no problem. It's right in the middle. They can do a level measurement and calculate that. Once it goes across that channel, then it becomes a little trickier. So now do you do multiple non-contact, maybe laser, radar, whatever, to get it out of the flow? That might be what you're going to have to do in that type of application. And again, you can kind of see how it narrows down, almost like a flume right there. Okay, so we get this all the time. What kind of maintenance is involved? Anytime you're using a non-contact ultrasonic, you really shouldn't have a lot of maintenance. Periodically to check that level is not a bad idea, but it's really not a major thing that you need to do. I would say monthly, quarterly, go out and give it a quick check. Again, the velocity verification calibration is not required. If you have a handheld and you want to go check it out, that's certainly up to you. Not a bad idea. I would just be a little careful that we don't get too crazy on that, because really the diagnostic on especially on the laser, will tell you, really how well it's working. We have tons of diagnostics on all the other stuff, and whatever equipment you get, you should look for that kind of capability, whether it's us or anybody else out there. And then some of the stuff that we're doing with the Doppler power readings and some of the error reporting that we're able to come back with are very, very beneficial when you look at that and say, can I bill for that? So again, a lot of money involved in billing, tons of money. You need to look at the technology that you can use to help your meter performance and really the accuracy. So how good is the data I'm getting? Well, the diagnostic will certainly help you, give you that information. And then what are you looking for related to your flow meter? So, you need to understand that. We didn't talk about mag meters today, or closed pipe, because we don't work with those, but same type of thing. If you have a closed pipe application, maybe a mag meter or propeller meter would be a better choice for you. But look at what your expectations are. And then your flume, again, see a lot of those out there, but not always perfect. You have Flumes, Weirs, they get dammed up, or they dam up flow. How much maintenance is that going to require? Am I going to be going out there every week to clean these? So need to, again, to determine what you're really looking for out there to get the best data for you. And finally, select the right technology for your application. That might be an ultrasonic with a flume. That might be a non-contact area velocity system. Could be any of those. So definitely feel free to get a hold of us, get a hold of your local rep or dealer, distributor, and they can help you pick the best technology for your application. With that, I'm going to go ahead and end it. My name is Rick, again, .dey, rick.die@teledyne.com. And you can certainly get a hold of me anytime you have any questions, comments, don't know, is this right or is this wrong? And I will certainly give you my opinion to the best of my ability. So with that, I'm going to go ahead and open it up for questions.
Well, thanks, Sharon. All right, let's look at, here's one that came in. We refer to 5% accuracy. Are we saying plus or minus 5%? Or does it flow get up to 95? So that's a great question. We're saying that we would be within 5% accuracy. But yeah, the way it's worded is a little bit confusing. Again, a flume or a weir properly installed, proper hydraulic conditions, you would expect to be within that 95% of real range. The laser has been verified to what we call MCERT class or class 2, which is better than 4%. So from a non-contact perspective, the laser is going to be in that 4% range. So anyway, good question. Okay, here's another one. Is an ISCO signature meter capable of taking multiple simultaneous level measurements from different sources? So anyway, yes, that's a great question as well. Signature technically could take 9 different inputs from different sensors. So in the case of what we had in that first Flume slide, we had a laser connected to the signature. We had 2 different ultrasonics that were also connected, and those can give input back to the signature. It can log it, report it, transmit the data if you want, and so on with a modem. But we're, again, seeing a lot more of those types of applications where that flume might work until it rains, and then they have surcharge conditions. Now all of a sudden, all bets are off. But you know, flumes again have been around for a long time. People like the fact that all they have to do is stick it with a ruler to get a level measurement, and away you go. So, but on that topic, another one that we get a lot of times is how do I calibrate my level? What's the best way? And really the best way, you know, you stick a ruler in the flow, provided your hydraulics are not real fast, you can get a good accurate level measurement. Another way would be going from the top down. So you go from the bottom of the top of the pipe to the water surface. And if you know it's a 72-inch pipe, you can do the math and accurately calibrate your level that way. So that's certainly another way to do it. That's a good way to do it. Another one would be with the laser, it actually reads the distance to the water. So it knows where it's physically located, and it knows the distance that it takes to hit the water and come back up. So if my pipe's 48 inches and it takes 2 feet to hit the water, I know my calibration. So it's very easy to calibrate the level that way. So another really good way to do that. Okay, let's see. When would I use a bubbler over an ultrasonic or submerged area velocity technology? Okay, good question. If I have a lot of steam, maybe foam, or a lot of turbulence, those are things that an ultrasonic sensor typically does not like. And that's one where a bubbler really doesn't care. So the bubbler doesn't know what's going on the top side. It's looking at what's going on underneath. And so if you have a wide range of temperature, and again, foam, steam, all that stuff, bubbler would probably be a better method for a level measurement only. They're also one of the more accurate level measurements. But if I have a lot of grease and things like that and silt that might plug a bubble line easier, then that might be where I'd want to go with an ultrasonic to keep me out of that flow. So different applications, and just kind of have to determine which one best fits what your needs are at that time.
Yeah. Hey, Rick, I'll throw in a comment on that as well, if you don't mind. And
Sure.
I would just say that that's the kind of the beauty of the signature product, is that it really doesn't matter what level measurement or flow measurement technology you want to use, ultrasonic, bubbler, area velocity, etc. The signature electronics supports all of those and could do so simultaneously or independently. And most importantly, it allows the customer the ability to be able to toggle from one technology to the other by making those changes quickly in the field, rather than having to remove the unit and return it to the factory for any modifications. So Rick's absolutely right. The level technology which is used really needs to be carefully considered based upon the source water being monitored. But the nice thing about the signature is it gives you the flexibility to do lots of different things with a number of different measurement technologies.
Thanks, Bob. Another one that came in while you were adding your comments was if I have multiple pipes dumping into a manhole, what do I do? And that's one that's not a good one. We've seen that before. I've seen it where water comes in from one pipe in the side and actually literally is going upstream. So the water coming into the manhole that they want to bill off of has two different velocity profiles. It's saying a very slow velocity on the one side, the other side it's saying, double or triple the amount of velocity. Bottom line, that's one of those, this is a bad application, get it out of there if you can. If you can't, then your best bet is to go ahead and take what it gives you, measure multiple points. If you're using laser, if you're using area velocity, then you get what you get, and you just go on down the road and do with what you can. So, but not an ideal application. If you run into that, if you can move and find a different spot, that's the way you want to go. Okay, I have one here that I get asked quite a bit to Manning formula. So I've been around, as Bob mentioned, multiple decades. I hate to say that, kind of. But yes, I've been around for a long time. And I've been around since Manning formula was kind of the thing. And so we have a lot of people that have used Manning formula in the past. And as a technical support guy, one of the questions I would ask is, okay, how accurate do you need to be? And they'd say, oh, not that accurate. This 5% would be good. They have no flume, no weir, no primary device at all. That was before area velocity. So all they had was a level and a Manning formula. Manning formula needs 200 feet, preferably 1,000 straight pipe, no bends, dips, tributaries, any of that. So Manning is the least desirable way to measure flow, and one that I would not want to have to go and defend if it became legal. So Manning formula is an approximation of flow, but avoid it if you can, and that's where the area velocity technology has come a long ways to replace that. So good question, huh? Let's see if we got any more here. A couple others popped up. Okay, one, let's see. How would a laser flow meter react if placed at a 90-degree bend with the manhole, assuming no remote Doppler? All right. So what it's doing is it's going to use the ultrasonic sensor that's typically mounted in the housing of the sensor. It knows where the water is right there, and then it's going to transmit based on that into the flow coming in. If I have a very drastic 90-degree bend, you might be hitting the bench with the ultrasonic. So that's not at all ideal. In that case, you might want to go with a remote ultrasonic, mount that where it's reading the level coming into the manhole, and then the laser doesn't care what happens behind that, and it can measure that velocity as it enters the manhole before it makes that 90-degree turn. That's as good as you're going to get in that type of application. All right, I don't see any other questions popping up, so I think we are, unless Bob, unless you have anything to add, I think we are about where we need to be on timing and everything, and just want to thank everyone for attending today, and want to wish you all a happy Merry Christmas and Happy New Year, and that's all I got for now. Sharon, Bob, anything?
Oh, absolutely. Happy holidays to everyone, and appreciate everyone joining us today. I'm sure that other questions will occur to you as you ponder this content and have a little time to think about it. So please do reach out to Rick or myself or anybody at Teledyne ISCO's product support group. And as always, we're happy and willing to listen to what you're working on and help you try to come up with some kind of an answer. So yes, thank you for joining us today, and happy holidays to everyone.